This is the video for sections 9.1 and 9.2 for Chemistry 1151. So in this chapter, we're going to be talking about acids and bases. And we want to go through what is an acid or a base. And there's a few different definitions of acids and bases. And the first definition was given by Arrhenius. And basically, Arrhenius says that an acid is something that contains hydrogen and makes hydrogen ion when it breaks down in water. So what we see here with this reaction, thinking about the states of matter, is if we have this gas, which would be called hydrogen chloride in the gas form, breaks down into aqueous, meaning dissolved in water, hydrogen ions and chloride ions. When we have it as hydrogen and chloride ions, we would call it HCl aqueous, and the name would be hydrochloric acid. Versus hydrogen chloride would just be the gas version. So now that it's dissolved, it's acting as an acid by this definition. A base was something that contains hydroxide, and then when it dissolves, it makes hydroxide ions. And so this is called sodium hydroxide. We're familiar with that. Just name it like it's an ion, and there's no change in naming or anything when it's dissolved. It just dissolves into sodium ions and hydroxide ions. This definition is a little limited and talks about H plus existing in water. But H plus doesn't actually exist in water because water, if we draw the Lewis structure of water and you think about the shape and the polarity of water, you may recall that water has this really negative oxygen and these really positive hydrogens. What do you think is going to happen when this really negative oxygen here sees this very full positive? This is just a partial negative, but it's going to see this full positive hydrogen. It is going to be very attracted to it. So attracted that these electrons, which I'll highlight here in pink, are going to go and they're going to grab that H plus. And that's going to make this thing, which is called the hydronium ion. I draw the Lewis structure for you. It has a charge because we added that H plus. So now we have an overall plus charge, and those electrons in pink, they made a bond to that new H. So I can highlight the new H here and here, kind of showing you what has happened. So when we talk about hydrogen ions in water, we're really talking about hydronium ions in water. And so you'll find in a lot of textbooks, and you'll find me say, oh, that's the hydrogen ion concentration in water, or the hydrogen, I'm counting the hydrogen ions in water. The more hydrogen ions there are, but in real life, we're looking at a 1-to-1 ratio of hydrogen ions and hydronium ions. And so when we're doing math, when we're thinking about, okay, what is actually going to be in my beaker of acid, it's never going to be actually hydronium if water is present. So if water is there, sorry, it's not actually going to be hydrogen if water is present. If water is there, it's actually going to be a mixture of water and hydrogen, which would be called hydronium. So Arrhenius is talking about this, but that doesn't actually exist, so we need a different definition. And the next definition is going to be more about what do acids do, and less about what do they make. So we're going to be using the Bronsted-Lowry definition. We talk about the job of an acid and the job of a base. And I'm going to make this, if you remember the jobs, it will make the rest of what we have to learn a lot easier. So donating a proton, or H plus, is the job of an acid. And we need to remember that H plus is just a proton because hydrogen just has one proton, one electron. If we take away its electron, it's just a proton. And then we'll call the base the proton or the hydrogen ion acceptor. And this is going to be more inclusive of different chemicals that we'll see, and it talks more about how it behaves and what it's doing, and less about just that one thing that it's making. And it allows us to use hydronium, which is the real life version of what's actually happening. So if we track this H, so if I draw, I think the Lewis structures are helpful here. So if I draw out these Lewis structures, and We see over here, we have that hydronium again. And then we have this chloride ion. All right, and I'm going to do some highlighting to help you see what we're doing here. This hydrogen was donated to the water. So we can kind of see in green, this hydrogen went to the water to make H3O plus. So H2O turns into H3O plus because that H, it's actually the H plus that's donated because these electrons, they actually move on to the chlorine. So where do they go? They go here. So they wound up on the chlorine. So the hydrogen didn't leave with its electrons. It's just the H plus that left. The electron that hydrogen had now belongs to chlorine because chlorine is very electronegative. So it says, hey, you can't leave with that. I'm stable now with these 8 valence electrons. You can't take that away from me because water is going to pull you over there. Also, water is more attracted to H without the electron because it's more positive, and that negative part of oxygen is going to be more attracted to the hydrogen if it's just a plus. Then we have these electrons. They made a bond to that H. And so essentially, this arrow is kind of deceiving, but essentially what happened is these electrons grabbed that H and these electrons moved on to the chlorine. If you're thinking about like what's actually happening, what's forming bonds here, that's really what happens. But I think because we're talking about the job of an acid is donated, showing you, hey, that H is going away from the HCl toward the H2O is a little bit easier to think about on just this basic level that we need to understand here. So who is the acid, who is the base? Well, HCl is the acid because it's the one that is donating the H. And water is the base because it's the one that is accepting the H. And so we can see in images this transaction. You see how here we have the H's are the little white ones, chlorines are the green ones, and you see over here the chlorines are all by themselves. All the H's that used to be on the chlorines are now on all those waters. We can see that extra white sphere on the red oxygen from just having 2 white spheres to 3 white spheres over here. So we can see that transfer in a particulate diagram as well. So if acids donate hydrogen ions, they have to have hydrogen in them. So we can define, or we can think about acids writing their formulas as something that has a hydrogen in it that can come off. Not every hydrogen is going to be able to come off of a chemical. So for example, if you have a Lewis structure like this, these 3 hydrogens are not going to be readily able to come off because this is a more nonpolar bond, and the carbon is not really pulling those electrons. Remember, in order to remove the H, those electrons have to be pulled to the other thing. And carbon is not really gonna want, think about it, these H's leave. We get carbon with lone pairs on it. Carbon doesn't like that, right? So, um, but now oxygen is really electronegative. And so if we have an option of this H or this H is the one that is acidic or the one that's gonna come off, it's gonna be this one because that oxygen can take those 2 electrons a lot easier. You don't have to get into the nitty-gritty details of this. Just know for our purposes, you're usually going to see the H in the front of the formula, but sometimes you'll see a formula written, especially as you move into organic chemistry, like in Chem 1152. You might see something written like this. This H over here for carboxylic acids, which are organic acids, are off to the right side versus in this class we talk about mostly H's in the front that are the acidic H's. But if you're unsure, draw the Lewis structure, see what makes more sense. Remember, to take away the H, you have to put those electrons on whatever the H is attached to and think about, would that atom like to have those electrons? Can it handle those electrons? Is it even electronegative enough to take those electrons? And if you're looking at carbon, the answer is probably no, those H's are not going to come off. If you're looking at oxygen, you're looking at like chlorine, those really fluorine, those electronegative ones, then yeah, the oxygens or the hydrogens can probably come off. When we're naming acids, we name them special. So acids are actually covalent compounds. They're all Lewis structures and they're sharing electrons, but they break into ions in water. So they're ionic, kind of, because they're making ions, but then they're covalent because they're bonded covalently together. So if you can see back up here in my example, we have covalent compounds, but then it made ions. And so we have to kind of deal with acids a little separately. We name them a little differently. Um, so what we do to name an acid is to look at the anion. So all acids have H plus. When we're thinking about naming, all acids have H plus as the cation. So let's think about breaking up the ions like an ionic compound and naming it based on the ions. So H plus is the cation. So we name acids based on the other part, the anion. If the anion has an IDE ending, we add a prefix of hydro, a suffix of ic, and the word acid. I don't know why that R is red. That's incorrect. Okay. So if the anion is chloride, then it would be hydrochloric acid. If you're not sure what the anion name is, think about it. What would it be with sodium? So for example, if I have NaCl, we would call that sodium chloride. That will help you get the anion ending. So we're talking about an acid of HCl, breaks down into H plus and Cl minus. And we know that in real life that H plus is H3O plus, but for the purposes of just writing and naming it, H plus and the other thing is the easiest way to think about the formula because H3O plus is not going to be in the formula. And so that's our anion. What is that called? If you're unsure of thinking about what that is called, put it with sodium. Oh, that's chloride. So we say if it ends in "ide," hydroic acid. So I have a saying that might help you. It's my ride, IDE, has hydraulics. That gets your hydro and your ic in there. So "ide" goes with hydro, ic. My ride has hydraulics. "Ide, hydro, ic." If that anion, so sulfate makes sulfuric acid. So if that anion is sulfate, it makes ic. So I remember this one by saying I ate something and it made me sick. I ate something, or you can say I ate something that made me sick. Either way, whatever you want, ate, ic. So if the anion ends in ate, the name is sulfuric acid. And notice that the formula goes with just kind of putting those two ions next to each other. You do your crisscross or whatever you need to get to make that, like you're writing it like ionic formulas, writing it with the charges balanced. If it ends in ite, we put OUS, acid. I remember this one for Sprite is delicious. So ite us. Practice writing and naming those acids. It is going to be very helpful for you. And it's really good right now in the end of the semester to go back over those polyatomic ions. Because if you don't know your polyatomic ions, you're really going to have a hard time naming acids with the 8 and the X. There are some other terms that you may come across. Monoprotic means one proton or one H. So HCl is an example of monoprotic. Diprotic means two protons or two H's, like H2SO4. Triprotic, right? We keep going. You know, you could have more. I don't know of any tetraprotic acids, but we do have mono, di, and triprotic acids. Bronzed lauric acids can be neutral, positive, negative. If you have an H that can come off as H plus, you can be an acid, a bronzed lauric acid. As long as you have a base there to take it, you can donate it. So thinking about those bases now, bases are proton acceptors. And a base must have a lone pair of electrons. So you've got to have something to grab that H plus, because if you don't have anywhere to grab it, you can't take it. Does that make sense? So if I'm thinking about the Lewis structure, I don't know why they didn't draw the Lewis structure for water if they drew it for ammonia, but let's draw the Lewis structure of water here. And then I'll draw OH out so we can see exactly what happened here. So this H is getting donated and it's being picked up by these green electrons. So the green electrons go and grab this H from water, or the water H is donated, right? So that means the NH3 turns into NH4, and it is acting as a base because it has accepted the H. The acid here is water. Water is acting as an acid because it donated H plus. And so what happened to these pink electrons right here in this bond? Well, here they are on the hydroxide. So they got moved to the hydroxide. But you got to have a lone pair. So like, could NH4 take another H? No, it doesn't have another pair of dots. So you have to have a pair of dots that can reach out and grab an H if you're going to be a base. And so if you're considering like, can this thing be a base or not? If it doesn't have a lone pair, it can't be a base. Most of the bases that we're going to talk about are bases that already have hydroxide in them. They're like ionic compounds that make hydroxide. Those are going to be our strong bases, or bases that have nitrogen in them. And so we're going to be thinking about those bases that kind of look like ammonia with the nitrogen and the lone pair that are going to take an H. You'll see some examples as we get moving on. You notice that water could act as an acid or a base because it has lone pairs that can take on an H, so it can become H3O plus, or it has an H it can give, and it can become OH minus. And then these are common bases. They have hydroxide in them, and so they automatically just make hydroxide in solution, and that is qualified as a base. The hydroxide looks kind of like water, but without that extra H. It still has those lone pairs on it that can grab an H to make water. So when we have an acid reacts with a base, we actually have a neutralization, but you can see here how the electron pair is moved over, stays on the A, the anion there, that base has these electrons, it goes and grabs that H, so we don't have these electrons anymore, they turn into here. So I've showed you this before, but this is just another generic way to look at it. Notice that what the acid makes is now going to be negative because it lost a plus. What the base is making is more positive now because it gained a plus. When we're talking about acids and bases, we also like to talk about what they make sometimes. And what they make are called their conjugate pairs. So the conjugate base of an acid is what you get when an acid does its job. So I can write that here for you. So the product formed by a loss of a proton from an acid is called conjugate base. Basically, it's what you get when an acid does its job. So if a job of an acid is to donate an H plus, if you take acid and you subtract H plus, what do you get? That's your conjugate base. That's the partner of that acid. It's what the acid is going to make. Again, the opposite would be the base. So the base's job is to accept. What you get when the base accepts is called the conjugate acid. So the conjugate acid is what you get when a base does its job. So it's really important to remember what the job of an acid and the job of a base is, and then you can kind of figure out these conjugates. We'll do more practice with this, of course, in class, but so the acid has HBr. If we get rid of H plus, we make Br minus. That's the conjugate base of the acid HBr. If we have a base of water and its job is to accept, we're going to add H plus. So if it starts with H2O, it'll turn to H3O and it's going to add a plus. So H3O plus or hydronium is the conjugate acid for water. Another way to think about conjugates is to reverse the reaction to get your conjugates. So who is acting as a base or an acid in reverse? So if we look at it in reverse, the bromide is accepting H plus. So it's acting as a base. But we can't call it the base because it's the one that's in reverse. So it's the conjugate base. The H3O plus is losing to turn into H2O. It's losing H plus. So that's acting as an acid. It's donating H plus, but it's not the acid of the reaction, it's the conjugate acid. So if you reverse the reaction and think about what am I doing going right to left, you can still use the jobs of acids and bases to identify your conjugates. Just make sure you know that the real acid and base are on the left side and the conjugates are the products. They're on the right side. Make sure that you also look at the charges when you're thinking about conjugates. So if I have water, if I say water is acting as a base, what's its conjugate acid? We're going to add H plus, and you have to remember that we're not just adding H. Anytime we are doing acid-base stuff, if an H is added, a plus is also added. So if we start with 0 charge and we add H plus, now we have +1 charge. If we're talking about an acid and we're losing a proton, we're going to subtract a +1 charge. So to make what's called the conjugate base here, just to put these terms back in your face so that you can help you memorize them. The acid does its job, it loses H plus. If it starts at 0 and it loses +1, so 0 minus +1, it's -1. Get out a number line. If you need to, losing positive is moving left in the number line, like subtracting. So 0 minus 1 is -1. Don't think about it too hard. We call something like water, you notice water could act as an acid or a base. We call it amphoteric. So it can do either. It just depends on who it's with. So if water is with an acid, it'll be the base. If water is with the base, it'll be the acid. Water is in the middle, it's neutral. And so it'll do whatever it needs to do depending on who it's with. All right, I will see you in class.